I know PER, I think since about 1997 or 8. Must have been some HPCA or something like this that we went together. And at that time you were also with Michelle, I think, so I met you both, and Josep was there. Um, and we kind of met occasionally at various conferences and various program committees. We started actually meeting a lot on program committees, and spending a lot of time in the Chicago Hilton. And yeah, not exactly the most fun part. So I'm very happy to have met him. And now that we are at PER-18, let's hope that it's going to look just the same at PER-28. No change. And I will try to tell you something. I mean, I'm very happy that I'm among all these architects. I love architecture, but I don't do it, or at least not anymore. So let me tell you something a little bit different. So it's about the architecture that is becoming, you know, more and more in some sense aggressive. That means it becomes very complex. The machines are huge. You need a nuclear power plant to run one. You need, you have accelerators of various kinds, including quantum now, that are extremely difficult to program, some of them even to understand, like quantum. There is an IoT, right, the World Wide Web, that are highly distributed, you know, you can think about hardware, pieces of hardware. And so what I have remarked, at least, I may be wrong, that what happens is the desire to do faster, cheaper, low power, and so forth is not by producing, I mean, has not been satisfied, or is not going to be satisfied by producing faster chips and faster devices, which it used to be, but by producing more of them and putting them all together. And that means parallelism, pervasive parallelism. And that's good, because, you know, if you have one hammer, everything is a nail. I know something about parallelism, so I love if you can do actually everything with parallelism. So parallelism is, yes, you can have hardware. All the machines today have a form or another of parallelism, from ILP or whatever to Blue Gene or something like that. But there are few really hardware techniques that can extract and exploit the parallelism automatically, which is kind of the holy grail, because you want it cheap, right? So we must use software. You must do software, use software at the application level and at the system level in order to manage this parallelism, the orchestration of huge number of whatever they are, threads, processes, and whatnot. So I was told to predict, you know, to use my crystal ball, which I don't have, but, you know, as I told you, you know, with the nail and the hammer, to predict what's going to happen. So what I predict is going to happen is whatever is convenient to me, that parallel software will be the most important topic for the next 10 years, right, from 18 to 28. What's going to happen after 10 years, I don't know. So in order to actually get this parallel software running on the hardware, there are several desiderata, several important issues. In order to do software, we need algorithms, because the software is only an implementation of some algorithm. But before we use or come up with better parallel algorithms, I was told so by some very famous theoretician named Leslie Valiant, we need to have performance models, because without performance models, we cannot evaluate which algorithm is better and which one is worse. So that's actually a very complex issue, and it has not been solved. There are no good parallel performance models. And I suspect that people will try, theoreticians, to come up with one, and not so theoreticians, to come up with one in the next 10 years. Hopefully it won't take longer than that. So here is your parallel software stack. It is the software development environment, so I think that we will make strides in developing some, coming up with some development environment. That means where you can actually develop parallel software. It's not the parallel software itself, right? In coming up with better algorithms. I will tell you a little bit more about each one of them. System software, very important. Use adaptivity at all levels because not one size fits all. And something that probably Yale would like, it is actually a bidirectional information exchange between the various layers. So many years ago, I wrote a paper, actually we wrote a paper, there is somebody else here in this room who wrote that together with me, smart apps. So there was actually a applications that had a bidirectional, if you want, information bus between the top level of the application and the runtime system and perhaps even hardware counter and so forth. So what the idea is that you don't need to know everything, but you need to set up the proper interfaces to get the proper information from one end to the other one and be able to, of course, not only read it, but control it. Now, what happens today in software development environments, right? There are two kinds of software development. Those that look today at serial codes and want to get parallel codes out of them. And various people have done over various times lots of stuff, like static analysis, compilers, dependence analysis, all this good stuff, you know, that you can, hardware guys don't like to study. They've done very well, actually, for instruction level parallelism, not so well, perhaps, at the loop level or thread level. I came up some time ago with a hybrid analysis, which combined static and dynamic analysis into under one roof, nicely smooth, you know, integrated. Results were very good, but I got more white hair, and I'm glad I still have some after all that exercise. So the alternative, manual parallelization. People write parallel code. They use MPI, they open MP or whatever it is, and they do it. And the results are okay, because that's probably the only parallel codes that we have. But they are horribly error prone. They're very expensive to do. It feeds actually a whole breed of developers, they name debuggers, and race condition detectors and so forth, which are really not that necessary, but that's what we have. So better compilers in the future might actually ease this burden, but it's a dead end, to my opinion. So I think that what we want to look at is more for new codes, what we're going to write from now on, not what we have written. So what we want, at least previous and maybe current approaches, is that you write the parallel program from scratch using some kind of an environment. We have also our own environment named Staple. It's a parallel program environment based basically on a library and a semi-language. I'm afraid to say that it is a language, because I'm going to get some Dane after me telling me that, you know, the language police. So what does the future hold? I think that in this area, it's going to hold actually a lot of excitement. It is probably one of the most interesting areas that is developing right now. To use a Swedish term, parallel languages, if you look at them, you know, it's like a Swedish breakfast, you know, it's everything. And I will show you afterwards a diagram with that. There are parallel annotations. Some people use that. Some people use an implicit parallel language, maybe not language, like OBS. It's very good for transferring from serial to parallel, so it is inherently a serially thought program that has been parallelized. Or explicitly, where you use dependence graphs as a constraint to something that runs fully parallel, fully distributed, like what we do. Domain-specific languages, yes, that's of course the latest rage, and I think that it will continue to be so, because it's customization. You can get, it has been shown, a lot of mileage, a lot of acceleration by using domain-specific languages. But it's not as easy as you might think, because domain-specific languages have to be designed, have to be proven to be correct. You need a full software stack for that. That means compilers, debugger, etc. And that's not for the faint of heart. So if we can find, I think that the future directions is to find a way to automate the generation of domain-specific language from some specification. I'm sure that you all at some point in your lives, I see here gray hair, but from those who have less gray hair, have taken a compiler class and used Flex and Python or something like this, automatic generation for parsers. Well, something like that, if we can use to generate new domain-specific language, provided that we know how to define the domain, I think that there is a lot of mileage left in that. The domain specific, it can be both to hardware and or to the particular application domain. So each new GPU, in some sense, has a domain specific language. This is your smorgasbord, right? This is your landscape. It is everything under the sun in various implicit, explicit libraries, languages, and so forth. We are also fitting somewhere there in red, just because, you know, I'm a professor, so I have to push my own thing. I mean, it has to be, you know, I mean, let's say you cannot do it otherwise, right? But I'm not going to talk about it, I promise you. So, specialization for custom. What time is it? Well, I didn't start it, so never mind.
6, 7 minutes.
Okay, fine. So, specialized languages for custom applications, I told it. So it is very difficult. What people do nowadays is they piggyback on an existing language. That's what they do. They have some kind of a simulator, translator from the domain specific to Java or to some other language. And then after that, they use the usual development stack, right, software stack. That is fine for experimentation. It is not fine for actually production code, because the compilers do not have access, direct access, to the domain-specific language. And that's where the knowledge lies. That's where the information is. So if you dumb it down and translate from domain-specific to generic language, then you lost all the good information in it. So all the optimization will have to be done either manually or not at all. So I suspect that compilers for domain-specific languages, and some of people like Kunle, Olokotun, and so forth, they do that, will hold a lot of promise to develop, you know, high-level compilation, high-level compilers that understand domain-specific languages. Is it easy? No, but, you know, we shouldn't do it just because it's easy, right? Should do it because it's harder. Domain-specific compiler is necessary debugging. That's another problem. You want to debug a domain-specific language without really any tools. You don't know what's going on. You translate it to some lower level. Then you really don't know what's going on. It's like I remember that C++ used to have a preprocessor named Cfront, and it would generate C. And then when you debug, you look at the C code. And good, I wasn't around at that time. So a lot more future work will be needed in this area. Language futures, for those of you who don't know, it's actually a real phrase, right? The level of abstraction will increase. I think that that's good because it eases programming, it increases expressivity, it lowers the cost of programming, provided, of course, that we have the tools. The codes, programs, will be generated from specification. We hope that will be generated from specification. For example, we use something named skeletons, actually it's some European invention. And sketches, the guy at MIT, Armando Solar, he's sketching programs, and there are various other things. It's just in a few examples. And they are, of course, in their infancy because they're not production codes and so forth, but eventually, hopefully, that's going to happen. So programming will become a much easier thing, especially for large systems. We need location and locality abstraction. It exists somehow. We use it also in Staple, a machine view, defining what locality is, defining a location. Defining a location in IoT, for example, good luck with that. Defining a location in a heterogeneous system that has GPUs and has various other accelerators as well as a regular CPU type of, you know, environment. Again, It exists somehow, but it has to be perfected. So, yes, would that be a problem 10 years from now? We hope not, but perhaps we have 10 years to work on it. Compose and conquer is my little invention. I'm not sure if it's an invention or not. So normally you say divide and conquer. I say compose and conquer. So if we start from building blocks, we can compose them into large programs with a few, I name it a handful of operators, composing operators. If we can prove that, or well, pick the operators in the proper way so that they guarantee certain properties when composing, when we can characterize the beginning building blocks and guarantee certain properties about those building blocks, how much power they consume, whether they are correct or not, maybe some security features, we can actually build a program and on the side perhaps have a shadow program of properties that can be composed and mathematically proven that they are some kind of a lossy sum of the properties of their building blocks. Don't get your hopes up. You're not going to prove that if these building blocks are correct, that the composition of them is also correct. But you'll probably sleep better at night. How to do this very well, it's difficult. So that's why it's something to be done. Parallel algorithms. Well, there is no substitute for a good parallel algorithms. That's why compilers never answer try the automatic parallelization question, because they can only extract the parallelism there was in the program. They could not actually generate parallelism. So we need, in this parallel world, we need to introduce, well, not to introduce, but to introduce everywhere, if you want, put everywhere asynchrony, because large systems will have to be working asynchronously. People like approximation. Large system probably can use some approximation, but it has to be carefully controlled and evaluated, not just say that if it is a red light and it misses a few dots in the red light, from these LEDs, that you can still recognize that it's a red light, that everybody can do that, right? So no human in the middle, right, between program and machine, right? Hierarchical algorithms, very important too, because they are related also to location and locality. If we can understand hierarchical and generate nicely hierarchical programs and hierarchical algorithms, that will have an effect both on the complexity, because sometimes you can drop entire activities, and certainly we can map it much better onto today's hierarchical machines. Polymorphic algorithms, more coverage is necessary. That means algorithms that are functionally equivalent but do it differently, right? You can say sort, and you can fill up this room probably with papers about different sorting algorithms, but you have at some point to choose also between them. So first you have to cover your universe, that's first activity, and then you have to select among them. We've done some work on it, but a lot of work is still left. AI probably, we've used it in the past, will probably be a very good avenue to make the proper selections. Distributed algorithms at exascale, non-trivial. Performance models. Well, BSP, log P, hierarchical BSP, not the easiest. I mean, it's not accurate enough. It's okay, but it's not accurate enough. The models need to account much more for data movement. They actually have to account for asynchrony, what happens in an asynchronous system where a lot of overlaps exist. May have to characterize power. They have to characterize locality. So a lot of things for theoreticians to do. I don't see any of them here, but it's a lot of them. MPI light is a desiderata, of course. It exists in some form, but there is no standard for it. MPI was so successful because there is a standard. The management of communication, these hybrid machines or heterogeneous machine, is complicated. That's something to be studied. The answer, should I put it in the system or runtime system, or should I put it in the application, various functionalities? It's a debate. It's almost a risk versus risk, but for the operating system guys. That debate continues. And I suspect that the pendulum will swing from one end to the other one and back. Adaptivity at every level is, again, not one size fits all. So you want to pick the right algorithm, you want to pick the right communication mechanism, various adaptive systems that I can send you to if you want to. Well, where do we go from here? To pervasive parallelism. So what do we, yeah. So abstraction and algorithms are very important. Asynchronous adaptivity is important, right? Distributed. Compilers need to generate and optimate code at very high level, right? Domain specific. The vertical, whatever. So if you allow me, I think that all this pervasive parallelism, right? Maybe we can come up with some new name for it here, right? It's a good place. It's a workshop. It's PER-18. So we can name it parallelism, not parallelism. So I would leave it at that. I did not want to underline because, we're going to put this up on the web and somebody, I'm going to make a fool out of myself. But at least for internal consumption, maybe you can think, maybe we all can vote on it. If this is a new word in the Webster's dictionary or the Oxford dictionary or the Swedish dictionary, I don't know. So, but I always end up with this one. If you're in the parallel world, think parallel and write clean code. Don't be cute. Just write clean code.
Thank you, Lauren.